All right, ladies and gents, lads and lasses, let's talk about waves. So, we learned what a wave was in section 1. Section 2, we're going to talk about the parts of a wave. So first we're going to start out with transverse waves. And they're fairly simple. They have a crest, which is the top of the wave, and they have a trough, which is the bottom of the wave. So crest, top, and trough, bottom. The other thing that all waves have is something called an amplitude. An amplitude is a measure of the amount of energy the wave is carrying. So the higher the peak on a transverse wave, the more energy it carries, and therefore the more amplitude it has. Amplitude is just a fancy word for energy. And notice amplitude is just a measure of the distance that wave goes beyond the normal, right? So if this were flat surface of water, the higher the wave, the more energy it carries, right? That's why a tsunami is worse than, say, a rock falling in your pool and making some splashes. So amplitude is how much energy it carries, and it's just the distance from normal. And that can be measured both vertically up and down on the wave, right? This is the same distance from the middle, it's just going down here. So up and down, our wave will have an amplitude. The last thing a wave has is a wavelength, right? And a wavelength is just measuring one cycle of the wave. So we go from crest to crest, right? If this is the start of the cycle, this would be the end of the cycle. So for every wavelength, we've had one cycle of the wave. We can also measure from trough to trough, although there's not a second trough on my screen right now, but crest to crest or trough to trough. Parts of a compressional wave are very, very similar, except instead of crests and troughs, we have what are called compressions and rarefactions. A compression is hopefully very self-explanatory. It's the compressed part, right? A rarefaction, on the other hand, is a fancy scientific word for the rest, right? So the non-compressed bits, the normal bits of, in this case, the spring, but it could be air particles, could be anything with a compression. So compression is the bit that's compressed, rarefaction is the bit that's not compressed. And then a wavelength would be measured from one compression to another compression, so from compression to compression. There is actually an amplitude on a compressional wave too, although it's not listed here. And the amplitude of a compressional wave is how thick the compression is. So the wider the compression is, the more amplitude that wave has. All right, let's talk frequency. So frequency of a wave is a measure of how many wavelengths pass a fixed point every second. Or in other words, how many cycles that wave goes through in 1 second. SI unit for frequency is hertz. So 1 hertz would be 1 wave per second, 2 hertz, 2 waves per second, 1,000 hertz, 1,000 waves per second. And the more waves we have, the more frequency we have, right? Because the higher the frequency means more waves in a second. Something to bear in mind, not all waves are created equal. So these two waves down here have the same amplitude. And remember, amplitude is the amount of energy a wave is carrying. So if we were to draw a line straight down the middle of this wave, right, it would be carrying the same amount of energy as if we drew a line down the middle of this bottom wave. They're both the same distance from the middle, so same amount of energy per pulse. But because this one has a higher frequency, because the top one has a higher frequency, it's carrying more pulses per second. So more energy is arriving at its final destination because more cycles are happening in a second. They have the same amount of energy per wave, or per wavelength, but the higher the frequency, the more of that energy can get to the end faster because it's more waves per second. So frequency is just a measure of waves per second, and it's measured in hertz. So again, 1 hertz is just 1 wave per second, 2 hertz, 2 waves per second, and so on. Here's just an example of that. So if we have 1 second and 1 wavelength, so remember we can go from trough to trough, not just crest to crest. So 1 wavelength, trough to trough, in 1 second would be 1 hertz. 1.5 wavelengths, 1.5 hertz. 3 wavelengths, 3 hertz. So again, it scales. Period. It says period is the amount of time it takes for 1 wavelength to pass a set point. So all period is the exact opposite of frequency. Frequency is waves per second. Period is seconds per wave. So we're just measuring how many waves, how many seconds it takes for 1 wavelength to pass. And the next slide just shows that. It says frequency and period are inverse of each other. So in this case, the top example here says we have 3 wavelengths, and we have it in a time of 1 second, so 3 cycles per second would be 3 hertz, and our period would be 1/3 of a second, because one wavelength goes in a third of a second. So down below it shows the formulas for those. Frequency is 1 over time, right? Cycles per second, waves per second. And period is the opposite. It's seconds per wave, or 1 over frequency. So you can find period by taking 1 divided by frequency, and you can find frequency by taking 1 divided by period. Frequency and wavelength. So it says as frequency increases, wavelength decreases. So the more waves we have, the less distance there is between them. That should make kind of a lot of sense, I would think. So high frequency would be very, very short wavelengths because there's not enough space to fit a lot in between them. It has to be wave on wave on wave. On the bottom there, we have low frequency, which means long wavelength. Lots of space in between waves because we don't have as many cycles. Wave speed, this is an equation we're going to use a lot, and it is fairly simple. The idea is the speed of a wave, or v for velocity, we're using them interchangeably, right? Speed and velocity, is equal to the frequency of that wave times lambda. And lambda is just a fancy Greek letter. We've seen some of those in science so far. And lambda stands for wavelength. So it's literally just distance in meters. You could replace that with a d and it would operate the same way. But velocity equals frequency times wavelength. So wave speed is measured in meters per second, or wave velocity, right? And that lambda is just meters. So frequency is 1 over seconds, lambda is meters, meters times 1 over seconds is 1 meter per second. So let's try it out. So it says, what is the speed of a wave that has a wavelength of 2.5 meters and a frequency of 170.5 hertz? So we just take wavelength times frequency, 2.5 times 170.5, and we end up with 426.25 meters per second. Relatively fast wave, right? Amplitude. We talked about this before, but amplitude is a measure of how much energy is in that wave. So we often call the amplitude the height of the wave, right? But technically it's just how far it is from the middle. So it could be both up and down, not just how high it is above. So if we take that middle, the higher we are above that middle or below the middle, right? Same distance here. That's how much energy the wave is carrying. In a compressional wave, the amplitude is measured by the compression, right? So the bigger the compression, or the greater the compression, the greater the amplitude of the wave. And that's it. Thank you for joining me with section 2.